Welcome to your AP Statistics Chapter 20 lesson on testing hypotheses about proportions. This is Mrs. Brown, and I'm here with Scott and Daisy, and we are ready to talk about hypothesis testing. Hypotheses are working models that we adopt temporarily. When we are conducting a hypothesis test, the first hypothesis we write is called the null hypothesis. It's denoted by H with a little subscript 0 and is referred to as H naught, or the null hypothesis. It specifies a population parameter of interest and proposes a value for that parameter. We usually write down the null hypothesis in this form: H naught, parameter equals hypothesized value. So, for instance, we might have H naught P equals 0.20. We want to compare the appropriate statistic from our data to what we would expect given that H naught is true. We can do this by finding out how many standard deviations away from the proposed value our statistic is. When we then ask how likely it is to get results like we did if the null hypothesis were true. The alternative hypothesis, which we denote by HA, contains the values of the parameter that we consider plausible if we reject the null hypothesis. So we want to think of a hypothesis test kind of like a jury trial here in the US. There is only a trial if the DA thinks someone is guilty. To prove someone is guilty, we must start by assuming they are innocent. We retain that hypothesis until the facts make it unlikely beyond a reasonable doubt. So even though we say we prove them guilty, we really don't. We just provide enough evidence beyond a reasonable doubt that they are not guilty. All right. Or we fail. If a person is declared guilty, we've just failed to show that we have enough evidence for them to be innocent. Okay. Then and only then, we reject the hypothesis of innocence and declare the person guilty. The same logic used in jury trials is used in statistical tests of hypotheses. There is only a hypothesis test if the statistician thinks that the alternative is true and the null is false. We begin, though, by assuming that the null hypothesis is true, and next we consider whether the data are consistent with the null hypothesis. If they are, then all we can do is retain the null hypothesis. If they are not, then like a jury, we ask whether they are unlikely beyond a reasonable doubt. The statistical twist is that we can quantify our level of doubt. We can use the model proposed by our null hypothesis to calculate the probability that the event we've witnessed could happen if the null is true. That's just the probability we're looking for. It quantifies exactly how surprised we are to see our results. The more evidence, the more surprising the data, and the lower the probability of having our data if the null hypothesis is true. This probability is called a p-value. A p-value is the probability of getting a result at least as extreme as the one we obtained in our data if the null hypothesis is true. So since our goal is to reject the null hypothesis, we don't want this probability to be high. You kind of almost want to think of it as the percent of doubt left in our mind. So we want it to be low. We want an extremely low percent of doubt. When the data are consistent with the model from the null hypothesis, the p-value is high, and we are unable to reject the null hypothesis. In that case, we have to retain the null hypothesis we started with. We can't claim to have proved it. In fact, don't use prove in any of your written answers about any hypothesis test ever. Instead, we fail to reject the null hypothesis and maybe state that the data are consistent with the null hypothesis. And so when they are in line with what we'd expect with natural sampling variability. Okay. a sample value, a sample statistic that's just a little bit different than the hypothesized statistic is not likely to provide enough evidence for us to reject the null hypothesis. There has to be enough of a difference to be called what is referred to as statistically significant. If the p-value is low enough, we'll reject the null hypothesis since what we observed would be very unlikely were the null model true. There's very little doubt that the alternative should be supported. If the evidence is not strong enough to reject the presumption of innocence, the jury returns with a verdict of not guilty. The jury does not say that the defendant is innocent, and they certainly have not proven that the defendant is innocent. All it says is that there is not enough evidence to convict, to reject innocence. The defendant may, in fact, be innocent, but the jury has no way to be sure. On the other hand, they may not be innocent, but the evidence wasn't strong enough to reject that presumption of innocence. Said statistically, we will fail to reject the null hypothesis. We never declare that the null hypothesis is to be true because we simply do not know whether it's true or not. We just haven't proven, or we never prove anything. We haven't provided statistically significant evidence to go with the alternative. In a trial, the burden of proof is on the prosecution. In a hypothesis test, the burden of proof is on the unusual claim, the alternative hypothesis. The null hypothesis is the ordinary state of affairs, so it's the alternative to the null hypothesis that we consider unusual and for which we must marshal evidence. There are four basic parts to a hypothesis test: the hypotheses themselves, the model, the mechanics, and the conclusion. So let's look at these different parts. The hypotheses, as we've said before, are two different hypotheses. There's the null hypothesis and the alternative hypothesis. To perform a hypothesis test, we must first translate our question of interest into a statement about the model parameters. In general, we will have H naught, or null hypothesis, parameter equals some hypothesized value. The alternative hypothesis, HA, contains the value of the parameter we would consider plausible when we reject the null. To plan a statistical hypothesis test, specify the model you will use to test the null hypothesis and the parameter of interest. All models require assumptions, so state the assumptions and check any corresponding conditions. Your model step should end with a statement such as, because the conditions are satisfied, I can model the sampling distribution of the proportion with a normal model. Watch out though, it might be the case that your model step ends with, because the conditions are not satisfied, I can't proceed with the test. If that's the case, stop and reconsider. Each test we discuss in the book has a name that you should include in your report. The test about proportions is called the one proportion z-test. The conditions for the one proportion z-test are the same as for the one proportion z-interval. We test the hypothesis H naught, P equals P naught, or hypothesized value for our population parameter, using the statistic Z equals P hat minus that value for P proposed in the null hypothesis, P naught, and we will divide by the standard deviation of P hat. And so our standard deviation here is going to be the square root of P naught times Q naught over N. When the conditions are met and the null hypothesis is true, the sampling distribution of the z-scores follow the standard normal model. So we can use that model to obtain a p-value. Under mechanics, we place the actual calculation of our test statistic from the data. Different tests will have different formulas and different test statistics. Usually, the mechanics are handled by a statistics program or calculator, but it's good to know the formulas. If you are going to use what is referred to as calculator speak as a substitution for actually cranking out the mechanics, you're going to have to label everything that you put in to your calculator, and we will talk about that later. The ultimate goal of the calculation is to obtain a p-value. Now, this p-value is different than our population parameter p or the hypothesized value in the null hypothesis, the p naught. This is totally separate. We're going to find p-values for every hypothesis test we do, whether we're doing a test about means or a chi-square test, we're going to find the p-value. The p-value is the probability that the observed statistic value or one more extreme could occur if the null hypothesis or the null model were correct. If the p-value is small enough, we'll reject the null hypothesis. If the p-value is low, we reject the null hypothesis. The conclusion in a hypothesis test is always a statement about the null hypothesis, followed by the corresponding statement about the alternative hypothesis. And that corresponding statement about the alternative hypothesis is a beautiful place to put your context. The conclusion must state either that we reject the null hypothesis because we have statistically significant evidence for the alternative hypothesis, or that we fail to reject the null hypothesis because we do not have statistically significant evidence for the alternative hypothesis. And as always, the conclusion should be stated in context. And again, that last part where you're saying your statement about the alternative, that's a great place to put the context. There are actually 3 different possible alternative hypotheses. We could believe that the parameter is actually less than the p naught, the hypothesized value. The parameter is not equal to the hypothesized value. We don't know whether it's greater than or less than. We just believe that it's different, okay? Or that we believe it's greater than the hypothesized value. When you are doing the two-sided alternative, the parameter not equal to the value, the p-value is going to be the probability of deviating in either direction from the null hypothesis value. So you're going to see what your results were and find where that lies on the horizontal axis. You're going to find the area to the right of it. And then you're going to reflect that same thing over to the left side of the distribution and find the area to the left of that tail. Now, if you use your CAS, all of this is going to be done in the background. But the thing that you have to remember is that a two-sided alternative is dealing with two tails. If you have a one-sided alternative, it's only going to deal with the appropriate tail. If it's a less than alternative, you're going to do the area to the left. If it is a greater than alternative, you're going to do the area to the right. Again, all of this is being done in the background when you use your CAS, but it's good for you to kind of understand. So if you believe that if the expectation is that there is a direction to the alternative, then that would be the way to go about stating your alternative. But since we are working problems that other people have created for us, you have to read very carefully to see if they just want to test for a difference, that would be two-sided, or if they want to test that the proportion is actually greater, that it's increased, or that it's decreased. You have to read very carefully to know which alternative to use. So, how small should the p-value be in order for you to reject the null hypothesis? It turns out that our decision criterion is context dependent. When we're screening for a disease and we want to be sure we treat all of those who are sick, we may be willing to reject the null hypothesis of no disease with a fairly large p-value of 0.1. A long-standing hypothesis believed by many people to be true needs stronger evidence and a correspondingly small p-value to reject it. Another factor in choosing the p-value is the importance of the issue being tested. You should always link your conclusion to the p-value. Um, and with that, you don't want to just declare that the null hypothesis is rejected or not rejected. You want to report the p-value to show the strength of the evidence against the hypothesis, and that lets the reader decide whether they want to um, reject the null or not. They can look at it and they may say, oh, that looks like a low p-value to me, and make a different decision than you. All right, so let's look at some examples. In the 1980s, it was generally believed that congenital abnormalities affected about 5% of the nation's children. Some people believe that the increase in the number of chemicals in the environment has led to an increase in the incidence of abnormalities. A recent study examined 384 children and found that 46 of them showed signs of an abnormality. Is this strong evidence that the risk has increased? First thing we're asked to do is to write appropriate hypotheses. So, since the standard, what has been expected to be true for years, is that the proportion is 0.05, we're going to write our null hypothesis as p equals 0.05. What people want to test, what people are curious about, the question of the hour is this strong evidence that the risk has increased? So that definitely has a direction to it. Our alternative is that the proportion is greater than 0.05. All right, we need to check the necessary assumptions, or actually check the conditions before we make the assumptions. All right, so three things. The simple random sample, is the population at least 10 times as large as the sample, or the 10% rule. We reverse how we talk about it. 10%, the sample isn't more than 10% of the population. That's equivalent to saying the population is at least 10 times as large as the sample. And then the success failure condition. All right, it's not stated that we have a simple random sample or random sample at all. We will proceed with caution, understanding that our methods make sense only if the 384 children are a representative sample of all children in the nation. There are more than 10 times 384, 3,840 children in the nation, so we're good on the 10% rule. And for success failure, we expect n times the hypothesized value of p. N times p naught is 384 times 0.05, which is 19.2 successes. And n times q naught, 384 times 0.95, and 364.8 failures, both of which are greater than 10. Please make sure you note that we are not using the proportion from the sample. We are using the proportion that's in the hypothesis, the null hypothesis, the 0.05. Because our model that we're building is based on being centered around, it's going to be a normal distribution centered around that null hypothesis value of 0.05. We want to perform the mechanics of the test. What is the p-value? Well, our p hat, which is not the p-value, is 46 over 384 is 0.1198. Okay, the p-value is the probability that we would get a sample proportion, p hat, of 0.1198 or larger if the true proportion p is 0.05, because that is our p naught, our hypothesized value. To find the p-value, go to the scratch pad, press menu and choose statistics. Under statistics, choose stat test, choose one proportion z-test, and enter the values requested. Okay, so we have p naught equals 0.05, x equals 46, n equals 384, and our alternative is that the proportion, the true proportion, is actually greater than the hypothesized proportion. All right, so we want to write this up. we are conducting a one proportion z-test. Our value for z is 6.28. Our p-value is approximately 0. 1.75 times 10 to the negative 10. Guys, anytime you get what looks like a value greater than 1, remember the p-value is a probability. You need to look and see. It's going to be multiplied by 10 to some negative power. That means that you have a p-value of essentially 0. It is very, very small. Explain carefully what the p-value means in context. If the abnormality rate has not increased, then the probability of observing at least 46 children with abnormalities in a sample of 384 is approximately 0. So if you look, this first clause right here, if the abnormality rate has not increased. So this is the null hypothesis. Okay, if the abnormality rate is still 0.05, that would be another way to state this. Then the probability of observing at least 46 children. So our results are results more extreme. And then we say what the actual p-value is approximately 0. So what's our conclusion? Due to our low p-value, and if you want to improve that by putting approximately 0 there, that would be great. But since we just stated that, we don't necessarily have to. It is a good idea to just to make sure you get credit for linking the p-value you just calculated to your response. So due to our low p-value of approximately 0, we reject the null. Okay, so we have linked our decision to our p-value. We just need to make a statement about the alternative hypothesis in context. So we have statistically significant evidence, since we rejected the null, that the rate of abnormalities is now greater than 5%. So I didn't just put P is greater than 5%. I said what P is. P is the rate of abnormalities. If you wanted to put the true rate of abnormalities, that would improve the answer even more, is now greater than 5%. So notice that I said we have evidence for this. You never put that we prove it. You don't state that it is greater than 5%. We just have evidence that it is. Do environmental chemicals cause congenital abnormalities? Well, the percent has gone up, but we don't know why. So we have no clue what the cause might be. We just know that we have evidence that the rate of abnormalities has increased. All right, let's look at another example. A startup company is about to market a new computer printer. It decides to gamble by running commercials during the Super Bowl. The company hopes that the name recognition will be worth the high cost of the ads. The goal of the company is that over 40% of the public recognize its brand name and associate it with computer equipment. The day after the game, a pollster contacts 420 randomly chosen adults and finds that 181 of them know that this company manufactures printers. Would you recommend that the company continue to advertise during Super Bowls? And then we're going to explain. Okay. Sometimes it's easier to actually, even though we write the null hypothesis first, maybe to think of the alternative. So the alternative is what we're trying to get evidence for. So the company wants evidence for the percent of the public that recognizes its brand name to be over 40%. So our alternative is going to be that P is greater than 0.40. The null will just be that it equals whatever that the value is. These two values in our hypotheses will be the same. You'll always have the equals in the null. You'll either have greater than, less than, or not equal to in your alternative. Okay, so you want to get credit for knowing what the parameter is. So you want to define what P is, where P is the proportion of the population, or you could just put the true proportion, that recognizes that the company manufactures printers. We will conduct a one proportion z-test if the conditions are met. So we need to check for simple random sample, the 10% condition, and success failure. The problem states that the sample was chosen at random. There are more than 10 and notice I'm showing all these calculations that it just seems silly to even show them, but it communicates that you know which values went to create the value of interest. So you need to show them. So 10 times 420 equals 4,200 adult Super Bowl viewers. Yeah, the audience is much bigger than that. Success failure. We expect n times p naught. So 420 times zero point 0.4 equals 168 successes. And 420 times zero point 0.6 is equal to 252 failures, both of which are at least 10. So our sample size is large enough. It's not too big and it's not too small. All the conditions are met, so we will conduct a 1 proportion z-test. Okay, so our value for z is 1.29 and our p-value is 0.10. So 0.10 really in a context like this would be considered large. Due to our large p-value, we fail to reject the null hypothesis. These data do not provide statistically significant evidence that more than 40% of adults recognize that the company manufactures printers. Thus, based on these results, I would not recommend that they continue to advertise during Super Bowls. Okay, so this, I did my full conclusion where I have an indication of whether the p-value is small or large and what that means in regards to the null hypothesis, and then a statement about the alternative in context of the problem. Then I have one more statement because this particular problem asks, would you recommend that the company continue to advertise during Super Bowls? So I'm going to actually answer that. No, I would not. Okay. So sometimes students are kind of frustrated because so far we don't have a hard and fast rule about what we're looking for a p-value for the sake of this course. Unless you were told otherwise, if a p-value is less than 0.05, we will consider that low. Okay. All right, guys, that's it. Go ahead and do the problems to try on your own. Thank you so much for your attention and for watching the video. I really appreciate that. I hope you have a great day, and you know how to get a hold of me if you have any burning questions.